Hi, this is Jeff Minter with Automotive Research and Design, and I'm here with another hybrid vehicle training segment brought to you by P10 Magazine. During this hybrid vehicle training segment, we are going to focus on hybrid vehicle diagnosis. Now, repair options are also becoming available for some of these inverter assemblies where you can actually replace internal parts. We aren't going to go over that today, but just be aware that it is becoming available from some manufacturers such as Toyota, where they're actually making some of these internal components available separately rather than having to buy the entire inverter assembly as one unit. So what's inside the inverter that we may need to diagnose? Well, if you take a look at the one on the left, these are both the same inverter assembly with different amounts of components removed from inside. And on the left hand side you'll see a second generation Toyota Prius inverter assembly where you can see the inverter bus capacitors that are displayed on the top there, the large black box. You can see that we have some orange wires coming out of the top of the photo here that would actually be towards the front of the vehicle. That is the AC compressor power wires that would go out from the inverter down to the electrically driven AC compressor. And then at the bottom right of the picture there we have the boost reactor. Now if you go a layer deeper on the right hand side where you can see that we've now removed some of the components from the top, you can actually see what are known as insulated gate bipolar transistors. These are the switching devices that actually generate the three-phase waveform that's going to be used to drive both motor generator 1 and motor generator 2. Now, surrounding a few of the bus bars within that unit where they actually have the three-phase output, you would also see, if you could zoom in close enough, you would see that we have current sensors around those phases so that the system can monitor the current flowing through at least two of the three phases. Now, you may see that there are current sensors on three of the phases, but in this case Toyota's only chosen to use two, where they then infer what that third current would be based on the fact that it is a Y-wound stator. It will always be using at least two of the legs. They can watch two of those legs, and based on the current that they're reading in those two, they can then make a calculation of what the third leg of that Y-wound stator would be carrying for current at any given point in time. To take a brief look at what else can be inside of these inverter assemblies, or at least what's commonly referred to as an inverter assembly, we're going to look at this 2004 to 2009 vintage Toyota Prius inverter converter assembly that's been removed from the vehicle. Now, as you can see, this unit's been pulled from the vehicle and it's actually been turned upside down. So this would be the part of the inverter that is normally towards the bulkhead. This would be the part that is normally towards the radiator core support, but of course it's been flipped over. Now, what you can see exiting the lower portion here in the screen is the DC to DC converter output. So this will be your 12-volt supply source that goes out to all of your DC loads for your 12-volt system, as well as your 12-volt battery to recharge it. So this unit inside of here actually replaces your alternator assembly and serves to recharge that 12-volt system. You'll see on the right-hand side that all of the components on the bottom part of this inverter are sourced from the same DC bus cables that go into the top of the inverter. However, they have a smaller set coming down to the bottom because this is going to be a smaller load area. Now, if you look towards the upper portion of the screen, you can see that we actually have a set of three smaller orange cables. These three smaller orange cables are going to go out from this inverter assembly down to the electric AC compressor and actually control the AC compressor operation. So this unit on the bottom section here is actually the inverter assembly that runs that electric AC compressor on this vintage of Toyota Prius. Now, what you may see in the future, and what we're already seeing in Toyota, is that they are starting to allow the internal replacement of some of these individual smaller components. That means if we have something as basic as a 12-volt charging system problem, we no longer have to replace this entire block, but we can now simply replace just the DC to DC converter section of this larger inverter converter assembly, which obviously will save some cost for the customer down the road. Obviously, if we're going to discuss diagnosing any component on the vehicle, we need to start by looking at the tools that will be required to do that diagnostic. Now, depending on what level of diagnostics you're going to use or going to get into, you may need some different tools. The tools that we're going to look at right now are going to be the scan tool, and we typically recommend an OEM level scan tool for hybrid vehicle systems just simply because the aftermarket tools do not work on all of the hybrid systems, so we can't make a blanket statement that all of the aftermarket tools will work on any of the vehicles. And you can't always access all of the control modules or get all of the data PIDs accurately out of those aftermarket tools. So we are still recommending an OEM scan tool as the best option. It's not the only option, but it is definitely the safest way to ensure that you're getting accurate information out of the vehicle. The second thing that you may need is an insulation tester. And the last one would be an oscilloscope. And if you're going to use an oscilloscope to diagnose an inverter assembly, we recommend a 4-channel oscilloscope, and you're going to need 3 inductive amp clamps, as we'll see when we look at how that gets hooked up to diagnose the vehicle. So what can you actually use a scan tool for as far as diagnostics that are related to the inverter assembly and the hybrid drive system? Well, the first and most obvious part would be the trouble codes. We can pull trouble codes out. This works as an excellent diagnostic starting point, just like it does on any other system. Just keep in mind that the code may not directly reflect the component that failed. Just like in other traditional automotive systems, the codes can sometimes be triggered by an outside failure that makes it look like that component's failed. The same holds true with an inverter assembly. One example would be if you had a motor generator failure or an electric machine failure that's actually causing the inverter to sense that it's flowing too much current. That inverter may flag a code saying the problem could be in the inverter, because they can't separate out the motor drive from the inverter assembly, or the drive motor from the inverter assembly. So the code will simply say it could be either or. The inverter just simply can't distinguish between the two types of failures. Now, you may also think that live data would be an option that would be helpful in diagnosis of an inverter failure. Unfortunately, the live data is somewhat limited for its usefulness in pinpoint diagnosis or root cause analysis on a hybrid drive system. This is simply because the data just doesn't refresh fast enough, and the fact that we can't really separate out components like I just mentioned between the inverter and the motor assembly. So when you look at things inside of the scan data function, what you're really going to be looking at in an inverter standpoint will be something like the inverter temperatures. That will give you an idea, especially if you have more than one motor assembly. You'll be looking at the inverter data PIDs to see if the inverter temperatures between both of those individual inverters that control the two motors are consistent. They are both cooled by the same cooling path, so we'd expect them both to have a relatively consistent temperature. Other than that, the data within that inverter assembly really isn't going to be able to pinpoint diagnose the system. The main reason for that really is the fact that the data refresh just isn't fast enough. For instance, if you look at the diagram that's shown on the screen here, this is a export from a Honda factory scan tool looking at the 3-phase motor current sensors that are on the inverter assembly. Now, while they have them available for display, they simply aren't usable as part of the diagnosis from a technician standpoint. If you look at that graph on the right, it should actually be a nice smooth 3-phase sine waveform. In other words, we should have 3 waveforms that look virtually identical if this vehicle is operating normally, and in this case they look absolutely terrible. The key thing with this is that actually came out of a vehicle that had no problems at all. The graph isn't looking that way because of a failure. The graph looks that way because the sampling rate is so slow on the scan tool that it simply can't keep up with the amount of data that's running through it from this hybrid drive system, so it ends up looking like a bad waveform when in reality that car was behaving perfectly fine. The next diagnostic tool we'll take a look at is something called the insulation tester. Now, an insulation tester is something you're probably already familiar with if you've been working on hybrid vehicles at all, because it's one of the few tools that's required by the OEMs for their dealers. So most aftermarket shops that have been working on these vehicles have also acquired an insulation tester. If you're not familiar with it, an insulation tester is simply a way to test the amount of resistance between the high voltage system and the vehicle chassis. There is a minimum resistance specification that must be met according to the Federal Motor Vehicle Safety Standard, FMVSS 305. That simply states that you must have at least 500 ohms of resistance for every 1 volt of pressure in that high voltage system. That has to be the minimum separation between the high voltage system and the vehicle chassis to ensure that we don't have a potential dangerous situation of high voltage leaking onto that chassis. What we would use this tool for would be to test to see if we've lowered the resistance below that minimum amount. Now, in most cases, the components will be significantly higher than that minimum amount because if you notice in this diagram, or in this block diagram that's shown here, it shows that we actually have a parallel circuit between all of the high voltage components in the chassis. So because a parallel circuit is always going to have less resistance than its lowest leg, even the lowest leg must be significantly higher than the bare minimum specs that are listed by the Federal Motor Vehicle Safety Standard. So we would then reference our service information, find the minimum specification, find the voltage that it's supposed to be tested at, and then we would use the insulation tester to actually check the amount of resistance that's currently available between the high voltage and the chassis. If you haven't done an insulation test before, this simple block diagram just shows how the connections would be made. You take your insulation tester, in this case we're showing a Fluke 1587 in the diagram, or at least we're showing a rendering of a Fluke 1587. And we're connecting it to the high voltage leads coming out of the power inverter and then to chassis ground. We would then set the meter at the appropriate voltage. For instance, in a Toyota system we would set it at 500 volts. We would actuate the test, and the tester will then show us the amount of resistance available between the high voltage component and the chassis of the vehicle. If you'd like more information on doing insulation testing, there's actually another P10 training segment specifically about using an insulation tester. One of the more advanced test methods for checking the inverter operation would be to use an oscilloscope along with 3 current clamps on the 3 cables that run from the inverter to the electric drive motor that we're testing. Now this allows us to see both the output from the inverter during motoring as well as the input to the inverter from the electric machine during a generating event. Now in order for us to be able to analyze the system, we have to know the condition of the motor assembly, because again, as I mentioned earlier, we could have a failure in the motor that makes it look like an inverter problem, or we could have an inverter problem that makes it look like a motor problem. Since bench testing an inverter is not something that's really doable at the technician level or in the service level, we're going to look at bench testing the electric machine first, or testing the electric machine as a standalone unit first. And then we would move into testing the inverter and electric drive machine together using this 4-channel oscilloscope. So if you look at how the setup is done on this one, we've attached some 4-gauge shielded jumper wires that actually allow us to wrap a current clamp around each of the 3 cables. Because the 2nd generation Toyota Prius has a bulk shielded cable assembly where you can't get around the 3 individual feed cables going to the drive motor, we've had to put some specialty jumper leads in. Once we're around those 3 cables with our amp clamps, we can then go ahead and take this vehicle for a drive, and we can record the waveforms going into and out of this inverter assembly during the varying operating conditions. What we're really looking for is how this inverter switches. Can it generate the waveforms that it's supposed to, and is it consistent across all of the channels or all of the phases of this unit? Now the equipment that we're showing here are the pieces of equipment we prefer to use. It is a Pico 3425 oscilloscope. That is a 4-channel oscilloscope, and it has inductive amp clamps hooked up to it from Fluke. Those are I400S amp clamps. This allows us to get a good quality signal with very little noise interference, and it has a very fast sample rate, so we can actually see the switching events that are occurring as the inverter is trying to create the waveforms that we'll take a look at here next. Now as we drive this vehicle down the road with the oscilloscope hooked up, we'd be capturing a pattern that looks something like what's on the screen, or at least we'd be hoping to capture a pattern that looks something like this. Now we aren't necessarily looking at the pattern for its overall shape. That's going to vary from one motor design to the next. What we're really looking at are a couple of different things, one being the switching aggressiveness, and we're also looking at consistency between the 3 phases. Now you notice we have 3 individual colors here. We have a red, a green, and a blue. Those are the 3 phases being displayed independently on the screen. This is why we need to have a 3-phase scope hooked up to this, or a scope with 3 phases available on it. So this way we can drive down the road, we can watch all 3 at once, and what we're looking for really is consistency in the amplitude and frequency to make sure that that inverter assembly is controlling the motor the way it's supposed to. Now in this case we see that they are very symmetrical, they have a very similar amplitude, and the switching on all of them, the amount of bumpiness at the top and bottom of the waveforms is very similar from one phase to the next. This is a good waveform pattern out of a vehicle that was operating very, very well. Now if you compare this waveform to the one that we just looked at, you don't have to be a really experienced inverter diagnostic technician in order to realize that there's a big difference between that last waveform and this waveform. You can see that we still have the 3 individual color traces. However, you can see that those 3 traces no longer look like each other. We no longer have symmetry between them. The shape of the waveforms changed from one phase to the next, and also the amplitude has changed drastically from one of the phases to the next. This gives you an idea of what we would be looking for if we had a significant failure occurring where this inverter is no longer able to draw a nice symmetrical 3-phase waveform to control that motor. Now obviously if we have a waveform that looks like this, we're going to have a vehicle that's operating very poorly. We're not going to have a smooth acceleration. We're going to have a motor that's running very, very rough. Just like we'd have an engine running rough if we had a cylinder that wasn't contributing equally, that would be a very similar effect to what we'd be seeing happen if we had an inverter waveform that looked like this. Inverter diagnosis is a very in-depth topic, as is the inverter operation as a whole, because they do a lot of very important functions within this electric drive system. So if you'd like more information on that, there is some more available through the other P10 hybrid vehicle content on their website, and we also have some on our website, which is gotohev.com, where we have some technical resources available in the form of webinar links that you can go to, as well as some technical articles that have been written over the years, many of which include some information on inverters. Or of course, you're always welcome to attend one of our training events where we have time to go into this at a much greater depth, as well as get some hands-on training time. Thank you for watching this hybrid vehicle training segment brought to you by P10 Magazine. Hopefully you'll join us for another future segment related to another hybrid vehicle technology.